Picture this. It's a lovely morning in your small hometown, and you've decided to go for a short stroll along the river. As you're walking, soaking up the warm summer sun, a beautiful white swan comes swimming around the nearest bend. And oh look, just behind it is yet another white swan. And then another. You, being the ponderous scientific sort, notice a common theme. All of these swans are white. And because these are the first swans you've ever actually seen, it's easy to formulate a little theory. All swans must be white. Then, almost right on cue, a fourth swan turns up. Lo and behold, it's also white. Well, that proves it. This theory is quickly becoming fact. But then something else crosses your mind. Hold on. How do you know a fifth swan won't turn up that's black? Or pink? It's impossible to discount that possibility, however unlikely it is. And here you thought you were just going on a calm, uncomplicated walk in the sunshine, yet unwittingly, now surrounded by this concerningly large number of swans, you stumbled across one of the trickiest questions in 20th century philosophy. How can we ever truly prove a theory to be correct? Luckily, these blinks to Karl Popper's philosophical classic, The Logic of Scientific Discovery, aim to solve this very question. Be it white swans or any other hypotheses you've been brewing on the side, you're about to find out why your theories might not be as airtight as you once thought. Okay, to start, let's go back to those swans. Once you're on your walk back from your riverside stroll, you get to thinking, how are you going to now explain your new findings that all swans are white to the world? I mean, it shouldn't be too hard. The evidence is on your side. You took a specific set of data, 4 swans, in fact, practically a flock, and you drew a reasonable theory from it. Every swan you've seen has been white, so therefore it's only natural to theorize that all swans are white. It's airtight. Who would disagree with you? This is an example of inductive reasoning, or simply induction. And Popper, the author, opposes this strongly. The problem is you're using singular statements, like this swan is white, to prove universal statements, like all swans are white. Logically speaking, Popper argues this approach simply isn't valid. It is always possible that a black swan, or a pink one, or a yellow one, might still come swimming around that corner. That applies if you've seen 4 swans or 40, or all the swans you can imagine. There might always be a black swan that appears. And here's a question. What would happen if a black swan actually did turn up? Well, that would then disprove the theory that all swans were white. So there's a bit of asymmetry to the logic here. Specific statements can't prove universal ones, but they can disprove them. And that's an important point when it comes to Popper's preferred scientific method, which is known as deduction. Rather than starting with specifics, deduction starts with universals and examines the relationships between them to see what other logical conclusions can be drawn. You might say, for instance, that all birds can fly, and also that swans are birds, and hence, you can deduce that swans can therefore fly. That's logically valid, Popper says, but that doesn't mean it's necessarily true. Rather, a good scientist would be constantly on the lookout for anything that goes against their hypotheses. They'd be looking to falsify their own theories. For instance, if they found out about a non-flying bird like a penguin, that specific case falsifies the general statement that all birds can fly. And that shouldn't be a disappointing result for a scientist. In fact, it should be exciting. It's an intriguing new piece of information that will cause them to formulate a better, more accurate theory. Instead of all birds can fly, maybe it's all birds have wings, And then they'll be looking everywhere for a bird with no wings to try and falsify that statement. In this way, falsifiability is a big deal for Popper. It's even what he calls the criterion for demarcation, the simple fact that distinguishes science from non-science. A statement is only scientifically valid, he says, if it can potentially be falsified. Otherwise, you're not dealing with science at all, but rather with something much vaguer, metaphysics. So, look, there's nothing wrong with saying all swans are white in the first place. The mistake is to think this is true simply based on the fact that you've seen a few white swans on your local river. Instead, you have to accept that your statement that all swans are white is only a guess. But even then, we're not out of the woods yet. That can still be picked apart by Popper. Because in order to still have that theory, guess or not, you have to think about how you even came up with that in the first place. How did you get the idea to suggest that all swans were white? That might sound like a trivial question, but it's not. Remember that Popper rejects induction very firmly. The existence of a few white swans isn't enough to justify the general statement. So there isn't actually any logical basis at all for coming up with a theory like our swan theory, or for that matter, even more legitimate scientific theories like gravity or relativity. It's basically guesswork. For Popper, coming up with a theory relies on a small but vital leap of faith, an act of imagination. He calls it psychologism. And it's something logic simply can't account for. And because of this, it's essentially outside the scope of what he discusses in his work. Popper's concern is with the logical processes that you subject a theory to. In other words, all the stuff that happens after you've come up with a theory. But he happily accepts this moment of imagination as a crucial first step. We just have to remember that that's all it is. A slightly illogical leap of faith is also involved when it comes to deciding which theories to accept as true. We can't use only our own experiences to decide what to accept, because, like before, that would just be inductivism. Instead, we simply have to make a decision. It's a bit like how a jury works in court. A jury is asked to determine what happened in a particular case. All it has to go on is the available evidence about the case and a pre-existing set of rules, the law. A jury's verdict is accepted as fact, but of course, if more evidence had come to light, they might have reached a very different verdict. So, is a jury's verdict the actual truth? No, not really. It's probably instead more accurate to describe it as close as we can possibly get to it. So, even though science aims for objectivity, it's essentially like a jury's verdict. It doesn't really deal in absolutes. It just makes the best guesses it can, based on the evidence available. For this next chapter, we're going to be dealing with probability. Because when addressing the idea of statements being either true or false, it's crucial to also factor in the role that probability might play in your reasoning. Take a six-sided die, for example. Say you want to roll a 6. Your probability of throwing a 6 is 1 in 6. So let's pretend we roll the die 600 times. You'd likely end up with approximately 100 sixes. But would it be exactly that? Likely not. You might have, let's say, 103 sixes rolled instead. So should you revise your starting theory and say that the probability of rolling a 6 is actually 103 out of 600? No, because our first statement was a numerical probability statement, calculated mathematically, rather than through experiment. Assuming the die is fair, the probability of throwing a 6 remains 1 in 6. The previous 600 throws don't affect that probability at all. And what that means is crucial for Popper. Probability statements are not falsifiable. Maybe if we could actually roll a die an infinite number of times, things would be different, but we can't. We simply cannot truly put probability statements to the test. So what role do probabilities have in science then? Popper, falsification fanboy that he is, says not much. Most of the time, since they're not falsifiable, they simply don't play a role. But, small caveat here, there are some occasions where probabilities really do have a role in theories. Brownian movement is one example, which is how particles move in fluid. The movement of liquid is somewhat random, so some deviations from average results are very much expected. And in a case like that, the variation becomes part of the theory itself. It's hardwired into the theory. So overall, a theory like that can, in fact, be falsified. It would be proved wrong if the results fell outside the window of acceptable outcomes. Because it's falsifiable, that then belongs in science. And Popper also makes another point about probability that throws a fascinating perspective on his views in general. What's the difference, he asks, between predicting the orbits of the planets and predicting the throw of a die? You'd probably respond that throwing a die is pure chance, whereas the planets move in a regular pattern. But Popper says that actually, the two scenarios are much more similar than you think, because it's all about initial conditions. We know the initial conditions in which planets move very precisely, through observations over many centuries. But precisely what movements go on inside someone's fist as they shake a die? What are the exact properties of the surface they're throwing onto? Throwing a die seems random, but only because we have such poor knowledge of the conditions. If we knew all that in detail, we'd be able to predict the outcome just as accurately as where Mars will be next Friday. And that would definitely help in a casino. There are some things, though, that we genuinely have no choice but to be uncertain about. At least, that's according to physicist Werner Heisenberg. In quantum mechanics, Heisenberg's famous uncertainty principle is all about the limits of what we can know. For example, at the subatomic level, the more accurately we know where a particle is, the less accurately we know its momentum. The most famous example of this is if we simply look at a particle. The act of looking at that particle causes a small exchange of energy with it, which then affects the way it behaves. In other words, there are really hard limits on exactly what we can know. It's not possible to continue getting more and more accurate in our measurements over time. It's only ever a matter of approximation. So, given what you've already heard about Popper's views on probability, it's easy to see why he was uncomfortable with Heisenberg's conclusions. Popper believed that scientists should be constantly modifying their theories to make them more and more accurate as they accumulate more information and knowledge. But Heisenberg says no. At a certain point, that just isn't possible. So, to cut a long and complicated story short, Popper disagreed so adamantly with Heisenberg's arguments that in the logic of scientific discovery, he actually proposed an experiment designed to falsify Heisenberg's uncertainty principle. But Popper's efforts came in for criticism too, including from Albert Einstein, and in later editions of this book, he modifies his position on this. It's funny, really, when you stop to think about it, because from one perspective, Popper and Heisenberg really aren't so far apart. What they have in common is an acceptance that it's essentially impossible to know anything with 100% certainty. It's just that, while for Heisenberg, that puts a limit on what scientists can hope to achieve, Popper says the scientists should never stop in their search for ever greater accuracy. For this last chapter, let's zoom out a little and think about what Popper's ideas really mean. And let's forget about the swans this time. I think you've got the picture with those. So, here's another scenario for you. Let's say tomorrow morning the sun doesn't rise. It just stays dark all day. And we're assuming, for the purposes of this, that you don't live in the Arctic Circle somewhere where this is actually plausible. The point is, just imagine something happens that is completely out of line with what you'd expect from the natural world. And assuming all the scientists managed to find their way to the lab, what should they do? It wouldn't be enough simply to explain why, in this one instance, the sun hadn't risen. The scientists would have to go right back to the drawing board and adjust all their existing theories about the way the world works in order to account for this one day's peculiar events. They'd need to find new scientific laws that explained not only the present but the past too, new laws that fit with all the evidence they had available. That one day when the sun didn't rise would be enough to falsify our current scientific theories. But remember, even once the scientists have made the necessary adjustments and come up with more accurate theories, every day that the sun either does or doesn't rise in accordance with those theories wouldn't prove those theories to be true, because that would be inductive reasoning. What those days would do is corroborate the theories, but that's much weaker. It's effectively just saying that there wouldn't be any reason for the scientists to be concerned. Because the moral of the story is really that science is always uncertain and tentative. Science isn't knowledge, it isn't truth. It's just as close as we can get to it. And when we encounter a result that falsifies what we think we already know, that's something to get excited about. Because it means we can come up with new theories that are ever so slightly better. So, what's the aim of science then? It isn't to uncover the absolute truth, because that's impossible. And after all, it's always possible that a black swan will come gliding down that river, or that the sun won't rise tomorrow. And in that case, we'll have to go back to the beginning and revise our theories from scratch. The aim of science is simply to become ever more accurate, and to do it better each time. You've just listened to Our Blinks to the Logic of Scientific Discovery by Karl Popper. The key message in these blinks is that scientists should aim to falsify their theories rather than verify them, so that they can revise the theories and make them more accurate. It's a mistake to think that science will ever uncover the absolute truth about how the world works. Rather, the aim should be simply to do a little bit better every time we learn something new. To implement this idea into your daily life, here's a quick piece of actionable advice to take with you. Falsify your own opinions. Popper's focus is on dense and complex scientific topics like quantum mechanics. But really what he's talking about is an attitude that can be applied in far less academic situations too. So, next time you form an opinion about something, whether you're scrolling through Twitter or listening to a podcast, don't just look for the evidence that verifies your view. Look for the stuff that falsifies it. That way, rather than getting excited when you see yet another tweet that confirms what you already think, you'll take an interest in something that challenges your views, and in doing so, pushes you to find a better, more inclusive worldview. Thanks so much for listening, and if you can, please leave us a rating. You can find the Rate It button on the screen right now. We always appreciate your feedback. See you in the next Blinks.